Right, we are back with question 1b, and question 1b is a kite. From what we can tell here, if I look at question 1b, if I look at the diagram in 1b, I've got quadrilateral MNOP, and it appears to be a kite, but there's evidence to suggest that this is a kite because if I look at the properties of a kite, I can see here that this quadrilateral has side MN and MP. They are the same size. These lines here, they don't mean parallel to. A lot of you say that, oh, this is parallel to that. That's not for parallel lines. This means they have the same size. So those symbols mean MN is the same size as NP. Okay, and we're using two lines here and one line here because they need to be separated. They are not all the same length, so we can't have two of these lines everywhere. Okay, so the fact that these guys have two on them means that NN and MP are equal, and they, or NO and PO, or if you want to name them ON and OP, doesn't matter in this case really, they each have this one line on them because it indicates that the two of them are equal. Now, if you look at the properties of a kite, it does say that two pairs of adjacent sides are equal. So, and it says are equal, not parallel. It says two pairs of adjacent sides are equal. So if I look at my kite, side MN and side MP, they are adjacent. Adjacent means that they are next to each other or side by side. And then the other pair is ON and OP. They are adjacent because they are side by side. They are not opposite each other. Okay, so one pair and another pair. So two pairs of adjacent sides are equal. So that is really an indication that this is a kite. I did mention in class that we don't really want to look at this problem because we did specifically not focus on the diagonals of a kite. Diagonals are the lines inside the quadrilateral that run from corner to corner. So ON and NP, they are diagonals, and diagonals are strictly dealt with in the grade 9 syllabus, which is why I never bothered to really get into that, although I did give you this problem to look at just as a challenge, which kind of forces you to take a look at the diagonal properties of this particular quadrilateral, which is a kite. If we look at the properties of a kite, we will notice that the diagonals, they intersect each other at 90 degrees. So in other words, this point here, where they intersect, that point where they intersect each other at 90 degrees, which immediately tells you that angle X over here must be equal to 90. And the reason for that would be diagonals of a kite. So if I go and make some statements over here, I didn't actually number the first one, but that was 1A. Kind of just randomly started over here. So this will be 1B. If I look at my kite, then I can immediately answer. So in this kite, we need to find the value of X, the value of Y, and Z. Okay. And just to confirm again, we have established that this is a kite. There's enough evidence here to suggest that this is a kite and not any of the other quadrilaterals. Okay, so we are in agreement that this is a kite. So I can say that X is equal to 90 degrees. I can make that statement immediately. My reason would be, and I'll throw the reasons up on the screen over here. That reason, if you can see, it says the diags of kite. So it obviously stands for diagonals of kite, but you can just say diags of kite. That is an acceptable reason. So X equal to 90 because the diagonals of a kite intersect at 90 degrees, but you don't have to write that entire statement. You don't have to say the diagonals of a kite intersect at 90 degrees. You can simply say diags of kite, and we will know obviously what you're referring to. So angle X is then 90. Okay, so what I'm going to do here, just to help the process along, I'm going to fill in the angles that we found so that it just helps us to find the others a bit quicker. This is in fact what I've been teaching in class, is to fill in whatever angles you find in your diagram, fill them in on your, even on your question paper. If you read through it on your page, fill in everything that you're able to fill in, because it does make your sketch or diagram more user friendly. So one thing to note here as well is when I've established that one of these angles around this point here is 90, it automatically means or follows that every other angle around that point is also 90, because angles around a point must add up to 360. So if one is 90 here, then because this angle and that angle is on a straight line, they must add up to 180 degrees. So if the one is 90, the other one must be 90. And because this angle and this angle is on this straight line here, they must sum up to 180. So if the one is 90, the other one must be 90. And so too for this one and this one, or that one and that one. So I hope you followed what I said there. Of course, you don't have to go and sort of prove this to yourself every time. You should know that if two straight lines intersect each other like this at 90 degrees, it means that every of the four angles around that point where they intersect is equal to 90. Okay, suppose they intersect each other perpendicularly. Right, so that means that I could just, because it's going to help me maybe a bit later, I could say that that's 90. I could say that this is 90 and that is 90. Oh, that's not 90, that's 90. Okay. So the next angle we need to find is angle Y. We could also find Z first if we wanted to. In class, I noticed how a lot of you were trying to figure out what to do to get to angle Z. The key was with getting angle X first and then realizing that every other angle around this point is 90. And the reason why you may be struggling with this a bit is because we did not cover diagonals of a kite or diagonals of quadrilaterals in class, and that is why the concept was a bit foreign to you, even though I did mention it afterwards. Okay, so once you figured out this middle part, then it means you've got the values for angles inside these four little triangles here, because in this triangle there's actually not a letter in the middle, but for this one over here, you already have two angles. You've got 63 degrees and 90. So to get Z, you of course would use the interior angles of a triangle that sum up to 180 degrees. So that is already one way of getting that. There was another way that one of you figured out in class. I won't get into that now. I think I'll just go for the most obvious one. At one of you, I think you know if you're watching this, you figured out a more elaborate way almost to get to Z, but we'll just go with this. I'm going to work out Z first then. So I can see that in this triangle here, 63 degrees plus 90 degrees plus angle Z must give me 180 degrees. So I'm going to make that statement. So I'll say there that I'll start with Z, so we can see that we are busy trying to figure out Z here, so I'll start with Z. So Z plus 63 degrees, which is that one there, plus the 90 degrees, which is this one here. All of that must be equal to 180 degrees, and my reason is interior angles of triangle. Sometimes I interchange this reason, which I maybe shouldn't. I should just stick to one thing, but sometimes I would say a sum of interior angles of triangle. I'm just being a bit lazy here, so I'm just going with interior angles of triangle. It is acceptable mostly, so yeah. A lot of you of course have already started to get into the habit of writing sum of interior angles of a triangle, so that is fine. I then continue to solve this equation, so that would be Z plus, that is 153 degrees. So I have Z equal to 180 degrees minus the 153, and to make sure that I do not make any kind of mistake here, I'm just going to pull out the calculator, or maybe not like that. There we go. I will say 180 degrees minus 153, and my answer is 27. So Z is equal to 27 degrees. So there we have Z. So coming back here, I can now fill in Z, which is 27 degrees, and then we still need to find Y. Now, having found Z in this triangle here doesn't really have any bearing on this angle Y. So we will have to look at this in a different way. Now, many of you, or quite a few of you, have noticed that angle Y is equal to 40 degrees. But for some reason, a lot of you could not really state the reason why. You knew that it was 40 degrees, but because your mind is fixed on the fact that this is a kite, you were trying to sort of grasp at reasons that has to do with a kite, and you came up with stuff like opposite angles of a kite, opposite sides of a kite, and all this weird stuff. But you need to realize that within this kite there are other shapes as well, and obviously the other shape I'm talking about is the triangles. And the fact that side MN and side MP are equal in size, and the fact that they of course form part of a triangle here called MNP, this would be an isosceles triangle, right? You of course can see that there are smaller triangles here, here, which we used earlier, and there. But we wouldn't need to be using these smaller ones here. You have to identify that these lines allow you to put these angles equal to each other because they make this an isosceles triangle. In fact, the kite that we are looking at here, any kite, it actually is made up of one smaller isosceles triangle and one sort of taller or longer one. Okay, so that is also isosceles because of these two sides. So that is an isosceles triangle. This is an isosceles triangle, and that is why angle MNP and angle MPN are equal, because that reason, of course, as we know from isosceles triangle, is angles opposite equal sides. In other words, this angle opposite that equal side, and that one opposite that equal side. That's the reason. So you can go and make that statement. You can say that angle Y is equal to 40 degrees. The reason is angles opposite equal sides. Some of you say or use the reason base angles of isosceles triangle. That is also accepted. So you can, I'll just add that here. Sorry, that's not right. Base angles of isosceles triangle. That would also be accepted. So there we go. We've got Y equal to 40 degrees, and we have found in the value of all the unknown angles for question 1b.